Haskell's foreign function interface allows us to import and call functions that are written in C. Now, if you have used this at all, you might know that you can import functions as safe or unsafe. And the usual advice is that safe functions can call back into Haskell, so you can go from Haskell to C, back into Haskell, but they are slow. And unsafe functions can't do that. So once you're in C land, you can't go back to Haskell. I mean, you can return, but you can't call a Haskell function, but they are much faster. And so the usual advice is, just use unsafe, right? Unless you really need callbacks. However, some people also advise the opposite, and actually the story is a lot more complicated than this. So in today's episode, we're going to recap the basics of the foreign function interface, and we're going to look at the differences between safe and unsafe functions in concurrent code.
Yeah, welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Yeah, so to start with, just a small recap of how the foreign function interface works, in case you haven't seen it before, or maybe you've forgotten. I have a C file here, which has two functions, sleepy and busy, and they both take three parameters: a length of time to wait, a number of characters to print, and the character to print. And what both of these will do, they have this little loop in there. They're going to print this character C n times, waiting s seconds in between every character. Now the difference between these two is that sleepy does this by calling a C, like a syscall, to sleep, whereas busy does a busy loop, like it spins, like it just has a big for loop, basically just waits a long time, keeping the CPU busy until roughly the amount has passed that you specified. So if I just copy this in here, how might we call these from Haskell? Well, we need to import them, just like you would import a Haskell function, but you need to foreign import them. So this is a foreign import. Then you need to specify the calling convention, and these days that is almost always C API. Used to be C call, that's kind of deprecated. Unless you have a good reason for it, just use C API. That's maybe a topic of another episode. For now, C API is what we're going to use. And then you specify the safety level and here. And so, for example, we can say unsafe here. Then you specify a header, which in our case is this episode 36, and the name of the C function. And then you need to specify one more thing. You need to specify a signature for the corresponding Haskell function. So in this case, we're just going to call the Haskell function sleepy also, but we could call this something different. And then we need to give a Haskell signature. So maybe we have a double and an int and a char, and then the whole thing lives in unit, IO unit.
Right. And here it's sort of our responsibility to provide the correct signature, right? This is not
to a degree. One of the advantages of C API over the old C call is that this does get verified. So if you get this wrong, you will get a type error at compile time. But that's within reason, right? So not all type errors are caught, but you get more than you used to. Okay. So we might do the same thing for busy. And then let's just try calling these functions. So maybe we could call sleepy. Let's sleep 1 second.
There's a quick question already, which we can just answer, I think, by Nicholas. Does that foreign import need language extensions?
Yes.
Actually, no.
You need to enable the C API FFI if you want to use that.
Oh, is that okay? Sorry. Okay, so because of C API, it does need one.
Yeah.
Because I mean, FFI itself is one of the few Haskell 2010 extensions, right? So it's like one of the few things which are different between Haskell 98 and Haskell 2010. But okay.
So yeah, I am actually using GHE 2021. So, but the C API extension, does need an extension. And we're also going to talk about interruptible FFI, which we'll talk about in a second. Also, that also needs an extension. So we're over and above GHE 2021, we need these two extensions, and there are others. I mean, that's completely related, of course.
Okay. Well, then it was very useful that we discussed this. Yeah.
Yes. Thank you for the question. All right. So let's call sleepy, and let's wait 1 second in between every character. Let's print 5 characters, and let's just print stars. And if I build this, why? Oh, okay. executable. Wait, why is this complaining now? All right, weird. Okay, anyway, it doesn't matter. And I then run it, and I don't want any output from Cabal. I just want the output from this, episode 36. And maybe I can run the whole thing through user bin time here. We see these characters being printed, like the stars. We get 5 stars, 1 second wait in between. And if we look at the output here from time, we told us it's 5 seconds. Okay, we make sense. And 0% CPU. And that's because sleepy is using a syscall to sleep, right? Whereas busy was keeping the CPU busy, right? So now if we build this again, I'm building separately because I don't want to include the build time in the time output. And we just run it again. We get roughly the same output. It's not quite the same, like it's approximating 1 second, but we'll see again 5 seconds, and now it's using 100% CPU, right? Because that's what busy does. Okay. This was just a recap. Now let's start looking at some more interesting things. So actually, what I've done is I have imported all of these 2 functions 3 times, and I've in separate modules. So I can just get rid of this, and instead of calling this, I can call unsafe.busy. In my unsafe module, I have these 2 imports that we just had in the main module. Now I also imported them safe, and I imported them interruptible. And this is something that is relatively recent in GHC. This is the other extension that I enabled in my Cabal file, right? Interruptible FFI. And I'll talk about what this is in a second.
But it is syntactically another sort of safety level that you can put into the same position as safe and unsafe.
Yes, right? You just put, exactly. You just put it here, interrupt. Okay, but let's stick with unsafe for now. And let's call this busy thing. Let's actually wait 2 seconds in between, and let's print 10 stars. But now let's try and time this out after 4 and a bit seconds. Right, so after 4 and a bit seconds, we should have seen the first star, actually the first 3 stars, right? Because we print the first star immediately, wait 2 seconds, next star, wait 2 seconds, the next star, and then after in a bit, right, that's the .1 here, the whole thing should cancel, right? And we're very used in Haskell that we can time out just about everything, right? So we would expect this to also time out just as anything else here. So let's actually run this. And so we see the stars being printed, and now the 4 seconds are up, but we don't see a timeout. Right, all 10 stars will be printed, and the timeout is not happening. Right, timeout is unable to actually interrupt this foreign function call. And this is one of the first important things to remember: is that both safe and unsafe functions cannot be interrupted. Like if you try and throw an exception to a thread that is running, is currently running, executing a foreign function call, they cannot be interrupted. The function foreign call must first terminate. And that kind of makes sense, right? Because the Haskell runtime doesn't know what the C code is doing. It could be doing all kinds of stuff, things that need to be handled and enclosed and terminated in a sensible manner. And so just killing it doesn't really work.
So basically you're saying now we're getting exactly the same behavior for busy, for unsafe busy, for safe busy, for unsafe sleepy, and for safe sleepy.
That's correct. That's correct. Yes, exactly.
Okay.
However, like Anders pointed out, we have 3 things, right, which were missing from what he just enumerated. And indeed, we can have interruptible FFI. So if I call interruptible.sleepy, oops, go on, here.
Missing an R, interruptible.
Interruptible, thank you. Now, if I run this again, we will see that it starts printing, and now the timeout does happen. So an interruptible FFI for a function call is indeed interruptible. And the way that that works is that the Haskell runtime will send a signal, in particular sig pipe, to the thread that's running the C code. So now it depends on what the C code is doing. In this particular case, the sleepy version is calling sleep, right? In fact, I can show you the C code here. It's calling this function useSleep here. Now, useSleep is a syscall, and when sig pipe arrives, it returns. And this is true for nearly all blocking syscalls in C, when a signal arrives, they almost always return immediately, right? And then errno is set to inter, saying we were interrupted. Okay, so when that signal arrives here, this will terminate or return, and then so I wrote this code, right? So I have to think about this too. I don't get it for free. I'm checking for this interrupt, and if so, I don't continue the loop. Right? If I didn't have this, then the signal would interrupt the call to use sleep, but then we would happily continue the next character. Now, this is not an episode on writing interruptible FFI, right? So, for example, if we happen not to be currently sleeping, but maybe we're currently putting the character, that signal will do nothing at all, right? And so this is not actually going to work, right? So this is just for demonstration purposes. Actually, writing good FFI that is interruptible is a whole topic in its own right. So this is just to illustrate the point. Now, in particular,
if I remark, I know you said it's not an episode on interruptible FFI, but there's a remark by Travis saying it is critical that the foreign code does not try to catch SIGPipe or other signals used by the RTS. Yes, that's right. So the RTS sets a particular signals and its own handlers for this. Messing with this is you have to really know what you're doing. Yeah, you have to be careful. Yeah, absolutely right. Okay. Now, in particular, when I call busy here, so busy, remember, was just this busy loop, right? It pins a character and it just counts up to a very big number. Now, if I try to interrupt this, like I run this again, then SIGPipe will still be sent, but there's no syscalls happening. Nothing is being interrupted. This is still not interruptible. Right, so this will still run to completion. All right. Okay. So now let's start thinking a little bit more about concurrency, because this timeout is basically a separate thread that throws an exception to this thread, right? So let's think a little bit more about what happens with FFI calls and concurrency. In particular, let's start a bunch of threads, which are going to, the first thread is going to print zeros, the next thread is going to print ones, and so forth. So let's spin up 10 of these threads here. And let's maybe, in all of them, let's call sleepy here. With 1 second in between every character prints, let's print 10 characters, and then I is the thing that we're going to print here. And then for the whole thing, let's just wait until everybody is done. Right? This is not normally how you would do this in a nice way, but for now, this will do. Okay. Actually, let's take one step back. Sorry. I also implemented this thing in Haskell. Right? So sleepy here, what does sleepy do? We just n times, print the character, and call thread delay. All right. So before we even think about the for a function call, let's think about the native case first. So we spawn 10 threads. All of them are calling a regular Haskell function that does exactly the same behavior as the C function, right? Has exactly the same behavior. And then we do the same thing here. Now, my question that I want to ask, if I run this code now, and I specify that I want to use exactly one core, right? So this n here, I mean, one core is not quite right, it's one capability, but you can roughly think of it as one core. How many threads are we going to see executing at once here? Right? I'm spinning up 10 threads, but I'm specifying precisely a one core, right? So the question is, how many threads do we expect to see? Do you want me to answer?
Well, you can if you wish.
I would expect, because okay, we basically see the answer already, but Haskell threading is not dependent on actual multiple cores, right?
Yeah, so exactly. So Haskell threads are green threads, which means that one core can execute any number of Haskell threads, right? And that's also one of the main reasons why Haskell threads are very cheap. You can spin up as many threads as you like, because they don't cost very much. Okay, but now let's repeat the experiment, but with unsafe calls. Right? So now we spin up 10 threads, and each of them are going to call the sleepy function, the C sleepy function, with an unsafe import. What do we expect to see now? Well, let's just try.
Yeah, I'm less confident there.
It's a much more complicated question. And we're seeing here, actually, only one thread is being executed. right? And it runs to completion. Remember, C functions are not interruptible, right? So once it starts, it will continue to run. And now the second thread gets scheduled, right? And the reason is that an unsafe foreign function call will block the capability on which it is running. So the entire capability shuts down. No other Haskell threads or C threads are running. It's just running just this C function now. So if I now run this with 4 capabilities, now we're seeing 3 of those happening at the same time. And the 4th one is the one that's actually executing the thread delay here. It's slightly non-deterministic. We could also see 4 threads all calling this one and this one being like not happening, basically. That's like depends on how exactly the scheduler works. Sometimes one, sometimes the other. All right. Does that make sense?
No, I think
now, finally, what happens with safe calls? Right? Again, same question. If I tell it I only want 1 core, how many do we expect to happen when I specify 1 core, but I still spin up 10 threads? And the answer might be surprising. It's all of them. And the reason for this is that when you run a safe, when you execute a safe foreign function call, basically what's happening is that it spins up a new capability to run that call, right? So you could have any number of capabilities, any number of cores being used for any number of foreign function calls. So this minus n, a lot of people think of this as, oh, I'm going to use n cores, right? 1 core. Actually, it turns out for this particular program, it was using 10. Like I have 16 cores on my machine here, it would use 10 of them, right? Because it spins up a new one for every function, for safe function call that I make. So that's something to keep in mind, that the behavior of these things is quite different. And this is also why safe foreign function calls are expensive, right? It needs to spin up a new capability, initialize it, etc. Now it can reuse ones sometimes, but it also needs to garbage collect them. So that's a very expensive operation. Whereas an unsafe foreign function call is literally just a jump. It just jumps to the address of the C function. Okay.
Do you have any intuition, by the way, like how much overhead the safe?
I don't. No, maybe I should have run an experiment on that. No, I don't.
Okay.
Yeah. Perhaps Travis does. Travis, if you have an intuition for it, leave a comment. All right. Okay. Now, we saw a difference between the parallel or the concurrent execution of safe calls versus unsafe calls. But what about native calls, actually? Right? We saw native, and we start with this one, and we saw, okay, it doesn't really matter, right? They all run in parallel because green threads, of course. But that was the sleepy version. What about the busy version? Is it the same here?
That depends on whether it's allocating, I guess.
Yeah. So the way that green threads work is it's called cooperative multitasking, right? Mm-hmm. So the threads themselves need to sort of indicate to the RTS, oh, I'm willing to like relinquish control now. And the way the Haskell threads do that is by whenever they allocate, right? So
in particular means that a thread that does not allocate is not really ever going to relinquish control.
That's right. That's right. So here we're seeing only the one of them executing at once, and with 4 we're seeing sometimes lots, sometimes only a few, sometimes we have to wait for a long time. Now it just depends on the vagaries of when GC happens to happen, when allocation happens, that when the threads get relinquish control, and therefore we can have multitasking. Now, of course, this is an unusual Haskell function, right? It's busy, like a busy loop. You would rarely have this in Haskell. Like most Haskell code allocates too much, not too little, right? Too little allocation is rarely a problem in Haskell.
You wouldn't write a busy loop, I guess, but you can potentially write some sort of you can be very clever, right, and design some expensive, in principle, expensive long-running computation, and you try very, very hard to make it non-allocating as possible, because
Yes.
in general that's good, but then you have
Yes.
weird concurrency implications.
Yes. Yeah. Yeah.
It's
If you try really hard,
it's a
it's
common
possible.
problem if you try to parallelize Haskell code. I mean, problem. I mean, not an unfixable problem, but a pitfall, right?
But yes, that's absolutely correct. However, you have to try really hard to write code that never allocates.
Yeah.
And we have a colleague, Duncan Kutz, who's pretty good at that. I don't think I would manage it for anything but the most trivial examples. Like it's hard. It's hard work. All right. So my point here is that it's not always completely trivial even for native Haskell code either. Okay, so we talked about the concurrent execution of multiple calls, but there is something else running in the RTS as well, right? We have the garbage collector. And so the question is, what happens in a concurrent program with the garbage collector? So let's run an experiment, actually. So I wrote a function called with lots of live data. And all this does is it just takes a number of how much data you want. And then it just generates that data and hangs on to it, right? Which means that the whole purpose of this is that whenever a GC is triggered, it takes a while, right? That's the only goal here. All right, so let's just indicate that we started here. Now I'm going to run a new thread, just one for now. That's all we care about. And it's going to run the native sleepy version here. And let's print a character every 1/10 of a second, so we see it a little bit faster. And let's print 100 of them and 100 stars here. So we start this thread. This is running the native Haskell code at the moment, right? And just going to print star, 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 star. Now, as it does that, we're going to wait in the main thread 3 seconds, then indicate that we are doing something here. And then we're going to call perform major GC. Now, if you haven't seen this before, this is just a way to, from your Haskell code, indicate, I want GC now, please. Right? Normally, we'd never have to do this, right? We just wait for GC to happen whenever it needs to happen. But if you want to, you can trigger it manually, right? So that's what we're doing here. And then when GC is finished, let's just indicate that it has. And then let's just wait another 3 seconds here, and then kill the thread that we're running, and just terminate. Okay. Now, the question I want to ask is, what happens to the thread that we spawn during GC? All right, so we spawn this new thread. It's going to print a character every 1/10 of a second. After 3 seconds, GC happens. What happens to this thread while GC happens?
Normally, the garbage collector in Haskell will stop everything, like in particular, a major garbage collection.
That's right. Any garbage collector. Yeah, so that's right. So the Haskell garbage collector is a stop the world garbage collector. So, and we'll see this now. Like, so this generate live data will take a few seconds. We'll see the thread being spawned. After a few seconds, we'll see GC happening, right? And we see that the thread has stopped. Like, we don't see stars being printed anymore. And the thread only continues again once GC finishes. Okay. This is as expected. Now, what happens with the FFI? So let's call the unsafe version first and run this again. Now, you might want to think for yourself, like, what do we expect to happen here? But let's just try it. So again, we'll take a few seconds to generate live data. Once we spawn that thread, it will start printing characters. It's doing that now. And then after 3 seconds, we'll call perform major GC. But the 3 seconds have passed, and the GC didn't happen, right? Only once the thread terminates does GC actually happen, right? And now we have the final 3 seconds, and then we terminate.
So even the thread delay of the 3 seconds happened only after the other thread happened, right? I mean, I think
this guy, yes.
No, the first thread delay. Because I mean, I think there was a noticeable gap between the final star and the angle bracket open.
Maybe in Prince, yes. I guess it depends anyway, on which capability they were scheduled. Yeah, it's possible. So yeah, remember, foreign function calls, both safe and unsafe, are not interruptible, right? Not by you and not by the GC. So when GC is triggered, maybe, I mean, in this case, we would trigger it ourselves, but maybe it was triggered because we were running out of memory. If there is a foreign function call happening, then GC needs to wait. Right? So this is something to be aware of, that a running FFI call might prevent a GC from happening. What about safe? Would this be any different? Remember, this is not interruptible, right? Safe. So we saw before, safe function calls are also not interruptible. So what do we expect to happen here? Let's run it again. We generate live data, takes a few seconds. All right, the thread starts. After 3 seconds, GC kicks in, maybe. And now we see something very interesting, right? GC starts, and the safe function call keeps running. GC finishes, doesn't matter. The thread still keeps going here. Right? So safe foreign function calls are indeed not interruptible, but they aren't interrupted here. Right? The GC just leaves them running. Unlike native Haskell code and unlike safe foreign function calls, unsafe foreign function calls, safe foreign function calls can keep running concurrently with the garbage collector. Right? And that's what we're seeing happening here.
Isn't that problematic, though? I mean, you said safe. The whole motivation for safety was that they can better interact with the Haskell world and call back and do all sorts of things. Or even if they just access data, I guess. Like, I mean,
absolutely. Yeah, absolutely. If this safe foreign function call is accessing data that might be touched by the garbage collector, all hell could break loose. Right? If this foreign function call is accessing memory that maybe gets deallocated or gets moved. Remember, the Haskell garbage collector is a moving garbage collection. Then we really are in trouble. And in fact, that's the last thing I want to show you.
Okay. Perhaps it's a good time in between to, like, Travis did actually comment on like his experience.
Okay, so Travis says, okay, go for it.
Yeah, in my experience, safe call overhead is 10 to 50 microseconds, which means thousands of instructions plus synchronization plus context switching overhead, while unsafe calls are 10 to 50 instructions, which means a handful of nanoseconds. So it's a pretty massive difference.
So this will be like 3 or 4 orders of magnitude.
Yeah,
makes sense. Thanks, Travis. Anything else?
No.
Okay, all right, cool. Okay, so for the final example, Anders was asking about safety, and indeed, we have to worry about that. So I just want to show you an example just for the setup here. What we're going to do is we're going to allocate a new byte array of 100 bytes. Then with mutable byte array, what this does is this gives me a pointer to a word date. All right, and if what I've done here in my C code, I have a version of the sleepy code here that takes the same 3 parameters that we saw before, but it also takes a pointer to a character, right? A buffer, like a pointer to an array, right? An array of characters here. And in addition to writing the character to the terminal, it also writes it to this buffer. And so this pointer to a character on the Haskell side becomes, where did I import it? I think safe. Becomes a pointer to word date. There's actually other options here, like this could be a mutable byte array hash thing that's unlifted FFI, which is yet another extension. But for the sake of this argument, for this presentation, this episode, we'll just work with the sort of old style pointers here. So this is a very direct translation to C code, right? A pointer to a word. All right. So what am I doing here? I allocate an array which is 100 bytes long. I then get a pointer to that array. I then call my C function here, which does exactly the same thing, except I'm waiting no time at all, and I'm writing 100 stars. Then once we return from the FFI call, we freeze the byte array and print it. So just to see that this all works as expected here, we just see the byte array with 42 stars here, and we see that also the output is here. Okay. This part is just like it's printing the value of the first and last element of the buffer. You can ignore this. All right. So now let's worry a little bit about what Anders was talking about, like what happens with GC and stuff that is on the heap. So let's again, I'll have some live data so that we can see a noticeable GC pulse. We don't need quite as much as before. Let's again indicate the start here. And let's maybe do the synchronization between our auxiliary thread and the main thread a little bit better. So let's make an empty envar, which the auxiliary thread is going to write to once it finishes. And then we'll start a new thread here. And then as before, we're going to get a pointer to the contents of this array here, call our sleepy buff thing here. But now let's just wait 0.1 of a second in between every star here. And then we do the same thing again. So we freeze the byte array here, and then we indicate to the main thread that we're done by giving it access to this frozen array. And then in the main thread, let's do what we did before. So let's wait 3 seconds, call, make sure that GC gets called here. Indicate that GC is done. And then we just read from the envar and print the result. And that's the end of our test here. And now let's run this. The thread starts, GC kicks in, and now something very horrible has happened, right? We segfaulted. Like, not that we didn't get a nice backtrace, we didn't get a nice crash, we didn't get anything, the whole thing segfaults. Like, it just crashes out completely, right? As a Haskell programmer, you never ever want to see this, right? Now, unfortunately, of course, working with FFI, you might see this more often than when you work with regular Haskell code. But what has happened here? Well, exactly what we were afraid of. Mm-hmm. We allocated some data on the Haskell heap, a byte array. We then took a pointer to that byte array, called a safe FFI function, then GC kicked in.
Descriptively named safe, yeah.
Descriptively named safe, yeah, exactly. GC moved that byte array someplace else, right? Because that's what the GC does, right? It's copying garbage collector. Everything that's live gets copied somewhere. But this thread didn't know about that, and so now it's writing to some part of memory that is completely random. And so this is very bad. So yeah, these safe FFI calls are not safe at all in the presence of GC or in the presence of concurrency. How do you fix this?
Yeah, okay. I was going to ask, can we fix this?
Yeah, we can. Yeah, and there's two ways to fix it. So when you think about it, when we call a C function, we either pass things by value, like an int or a char or whatever, right? Those things get copied to the stack. That's not a problem at all, right? The difficulty only happens with pointers to stuff that's on the heap. Now, there's two ways to fix it. We can either make sure that this is a memory, which is not managed by the GC at all, right? So rather than allocating a byte array, you could call malloc from Haskell. Now this is allocated on the C heap. The GC does not even know about it. It's unmanaged, right? And so it won't get moved. The other option is to allocate what's called a pinned byte array. So a pinned byte array is under the purview of the Haskell runtime. It knows about it, but it promises never to move them. Right. So instead of using new byte array, we say new pinned byte array. And now when we run this again, this whole thing will just run just fine. The segfault disappears. Now, the one thing I want to mention here, and then we'll finish the episode, is that even with pinned byte arrays, you still have to be careful. Like, for example, suppose that we would not actually use the buffer anymore after we're done. So maybe we're just indicating by unit, and then we're not actually using it anymore. And maybe instead of this with pattern here, maybe what we can do is we would instead just ask for what that pointer is. So that's a different function called mutable byte array contents here. Mutable byte array contents of the array. like this. Right? So this also is this type safe. Now, this is basically the same thing. Like this is exactly what that with pattern gives you. However, now there is no dependency anymore here, right? There's no scoping anymore. GHC could move this up. It could say let C array equals this thing here, maybe even a bang here, and then we have a C array here. And now the difficulty here is that this is just a pointer, right? It's not a root. It's not a GC root. Like it's just a raw. It's just a memory address, like nothing else. Pointer is literally just a memory address. So if a GC would kick in now during the execution of this thread, it's possible that this pinned byte array, even though it's pinned, might get deallocated because it's not used anymore. And if it's deallocated, of course, we're in trouble again. Now, the way to fix that is to make sure that it's still live in some way, right? And so the with pattern ensures that it's at least live for the scope of your call to with byte array contents. But also, if you just use array here, like normally you would, right? Normally you would pass a buffer, somebody writes to the buffer, then use the buffer afterwards. You'd also be fine. But yeah, it is something to be aware of. Anyway, that's all I wanted to show.
Travis has one more remark. I guess to me that was kind of clear, but I think it is nice to spell out. So I mean, so in a way, like the segfault is not the worst thing that can happen because, like, I mean, basically, like if no segfault happens, it can end up even worse, right? Because like it can like happen that stuff gets moved around. You effectively write somewhere, Haskell heap memory gets corrupted, and you will get some sort of extremely difficult to debug behavior or crash at another place. So
yeah, absolutely.
It's
so I think I can even show this. So I've restored this back to the version where we didn't use pinned data here. Now, if I tell this to use more cores, like this doesn't always segfault. Sometimes it just runs. Okay, in this case it did segfault. I can try it one more time. Like it's non-deterministic now, but no, okay. All right, doesn't matter. If you run this often enough, if you get lucky, then it will just keep running. And at the end of it, no segfault has happened. But if you then look at the contents of that buffer, it's something completely unrelated. And indeed, like Trevor said, something else somewhere got overwritten. If that is somewhere like on your Haskell heap, which is still alive, well then like it's completely unpredictable what has happened. So yeah, absolutely. Lots of fun to be had.
So is there, I know we are over time, but is there some sort of final summary advice you would want to give after all this?
So unsafe are fast, can't call back into Haskell. We know this. Safe is slow, get a new capability. Okay, fine, we know this also. Unsafe functions block the capability, right? So if you have something that runs for a very long time, you might not want to make it unsafe because you might block GC, and therefore the whole thing, like that's something to think about. Where safe functions don't block the capability. However, you need to be extremely careful, right? So because we see like this movable of stuff being moved around. So my rule of thumb is use unsafe unless you absolutely cannot. And the reason, like, why might you not be able to? Well, maybe you need to call back into Haskell, then you have no choice. Or it's such low running that the blocking of the GC is too much of a overhead. In that case, use safe, but then be extremely careful. Use pinned data or unmanaged data memory. Be careful with these things. And remember that even safe foreign function calls are still not interruptible. So if you need interruptibility, you need to have an interruptible foreign call, which behaves like safe in other ways. But then you have to do a lot more work on the C side also to make sure that your code truly is interruptible. And then you have to worry about resources get allocated. Like if you, in your C code, allocated some resource, maybe a file handle, and you get interrupted, how do you make sure that this gets deallocated again? Yada, 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 right? So that's a whole different problem. Yeah. No easy answers here, I'm afraid.
Oh, okay. I mean, sometimes things are difficult. Yeah.
Yeah.
All right. Yeah. Thanks for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. And feel free to leave further comments below. We'll leave the chat open for a little while, but there hasn't been that much discussion, so we're probably going to close it soon. And yeah, we'll be back in the beginning of December, most likely. Right? Thank you very much.